Okay, we're back to the Thursday edition of the continuing soap opera, Learning Mathematics and Trying to be a Roboticist. What's going to happen next? Okay, so I had a great trip to Georgia Tech, but I got to bed at 2 a.m. because of weather delays, so I'm going to be calling upon your energy again today, just like I was on Tuesday. You're going to think I'm a vampire here pretty soon, okay? I need your energy. So we're getting to the point where some of our abstract nonsense is actually going to start leading to results. So the next 3 lectures, I think you'll find them to be empowering and making use of all the material that we've learned. So just our usual quick review session. The main thing we learned about on Tuesday was the notion of a norm. So this is a way to measure the length of a vector or the distance between 2 points in a vector space. So if we have a vector space with a norm, we call it a normed space. And for doing this in Rob 501, we are restricting the fields to be the real numbers or the complex numbers. There we go. Come on. So the norm has to satisfy, it takes on non-negative values, and it's 0 only for the 0 vector. Otherwise, you get semi-norms and pseudo-norms. The triangle inequality has to hold. For any pair of vectors, the norm of the sum is upper bounded by the sum of the norms. And then it plays nice with scalars. A scalar times a vector has length that is exactly equal to the magnitude of the scalar times the norm of the vector. So it plays nice with scalars. We use this to define distance between 2 points. Not so interesting. Much more interesting, the distance between a point and a set of approximating vectors. So that distance is the infimum over all possible vectors in S I might use to approximate X. And you can also write it then, since we're in a norm space and not a metric space, the infimum of Y in S, norm of X minus Y. So it's minimizing the approximation error. And we drew a picture to show that you're also solving what is called a minimum distance problem. How far is X from the set S? You just look at all points in S and you look at their distance and you take the smallest one, if there is a smallest one. If not, you take the infimum. We talked about this ubiquitous notation. It's everywhere, though it's not used with great care everywhere. So this is the cool and educated way to write down that you're solving an optimization problem. So if you want to seem in the know, okay, you write X star equals argmin. So argmin just makes you seem sophisticated, okay, so that's always good. But the problem is it comes with some understandings that people sometimes sweep under the rug. So when I say this, first of all, the solution to my minimum distance or best approximation problem, it must be in the set that I was talking about. That's easy. But it also needs to be a solution of this problem, and there can't be another one. It has to be unique. So often people will write this down when they haven't proven that a minimum exists. They'll say argmin, and maybe there's not one. Okay, so there should be at least one. And the other part is there should be only one. Otherwise, the equal sign should be an element of, because this should be all of the possible solutions. Okay. Then we had a whole bunch of different examples of norms on n-tuples. We have the p-norms for p be greater than or equal to 1, strictly less than infinity. We have the max norm or the infinity norm or the sup norm, where you just take the largest entry in the n-tuple in terms of magnitude. And since it's a finite set, max always exists. Another interesting example is you take two real numbers, one less than the other. So they're real numbers, they're not infinity. Could be very, very negative, could be very, very large, but they're finite. Take that closed interval, take the field to be the reals, and take all functions from that set into the reals that are continuous, and we haven't defined continuity, but use your intuitive notion of what continuity is, because you've done a calculus course somewhere. Then the p-norm on functions is the same thing as here. Instead of sum, it's a sum. Okay? That's what an integral is, to the pth power. And then you take the pth. Whoops, there should be a 1 over p there. 1 over p. So 1 over p, so p between 1 strictly less than infinity. And then the max norm, sup norm, infinity norm equivalent is you take this sup of these continuous functions. We will prove towards the end of Rob 501 that that supremum, there is a value to it, so the maximum actually exists, and so it's also called the max norm. But for right now, you're just taking that on faith, that actually exists. So those are all ways to measure lengths of vectors in different situations. Question?
So, for the argument thing, what situation could there not be? If there's anything in the set, something is the closest one, right?
Well, yeah, so what if you're doing x star is argmin, the function is just x, and S is the open interval 0, 1. There is no minimum. Yeah. So there's lots of cases where the infimum, okay, we have it set up so the infimum is always defined, but the minimum may not exist. And I'll draw a picture a little bit later where there's an infinite number of solutions also that are minimizers. So it's not a unique one. So all those things are possible. And this is just more an awareness thing, just so you realize the notation comes with consequences, but people tend to use it as, this is the problem I'm trying to solve, but they don't really make it precise because they haven't talked about this part, they haven't talked about the unicity and things like that. So, a little bit of laziness in the field. Does that shock you? It should. It should really make you mad, but I know. No, nothing shocks us anymore today. We drew this picture that was intuitive to us when we're working in the plane, I think. So if our set of approximating elements is a subspace, or the thing we're trying to calculate the distance to is a subspace, a line in R2, and if I just put a point here, and I ask you, what is the minimizing element and does it exist? And if I point to this one, you go no, and I point to this one, you go no, point to this one, you go no, and I point to the one that's directly giving me a right angle, you go yes, okay? Okay, so it's true in R2 when the norm is the sum of the first component squared plus the second component squared square root. This is the minimizing vector, okay? It's characterized by the error vector is a right angle to the subspace that you're using for your approximations. Okay, so this is the picture when we're in R2. X star is argmin x minus m over all m in a subspace. Notice 0 is in here. Yay! Okay, 0's in here. And then we will write that. I'll formally define this, but one says x minus x star is perpendicular to m or orthogonal to m. So we didn't have this notation on Tuesday, so you can write that down. So that we're going to make that picture formally correct. What does it mean that two vectors are the A vector is orthogonal to a subspace when you have functions, when you have matrices, when you have all that stuff? Whoops. Drawboard Pro. No, I don't want Drawboard Pro. This is just a review because we will introduce the notion of this new type of operation called an inner product. I'm going to emphasize over the reals, but I'm just popping in the review of complex numbers. We don't need to pay any attention to this in lecture. You can just read this afterwards. So just leave yourself some space to say, hey, go online and copy in the few facts about complex numbers. And this wasn't on Tuesday either. Okay, that's why the little funny face next to the recall? No, well, not really. But yet many of you have seen a formula like this somewhere. And so I want this picture in your mind when I do the abstract stuff. And if you relate the abstract stuff to this, I think your life will be much better. So you take two column vectors, so n tuples with coefficients in the reals. So the transpose of x is a row vector, y is this column vector. When you multiply them, this is the rule of matrix multiplication. It's just the sum of the ith coefficients. Now, did you have a name for this in one of your courses? Dot product. Okay. So I'm not putting a name on it here. You may have had one, that's fine. Now, this is why it's useful. You recognize these two vectors as being orthogonal from my beautiful picture that I pre-drew, because there's no way I could draw this live in front of your inquiring and demanding eyes, okay? So here's two vectors in R2, x and y. And when I calculate x transpose times y, I get 1 times minus 1 plus 2 times a half. And I get 0. Okay, so I have an operation on pairs of column n tuples that I can say is equivalent to this notion of a right angle and being orthogonal. So that's what we're going to build on right now. Okay? So if I just do this product, I'm not giving a name to it yet. You guys sometimes call it dot products. We're going to call it something else. You get 0. Okay? This and this is what we're going to make precise right now. Excited? I should be. You're not excited? Something's wrong with you. How about that? Definition. Let X, R be a vector space. So that statement alone used to reign terror in Rob 501, and now everybody's going, no problem, got it, okay. A function that we're going to denote by a pair of brackets, and it has two dots in it because it takes pairs of vectors and maps them to the reals, okay? You'll get used to this really quick. Right now it seems kind of crazy. The dots, just like when we put two bars and a dot, that's where you put argument 1, that's where you put argument 2. This is an inner product if the first thing, I take any two vectors in my vector space and I do the inner product of x and y, I get the same thing as if I flip the order of the arguments. Okay, so x transpose y, I can flip xi and yi, that means I can flip x and y, it just doesn't matter, okay? So it's all the same. For every pair of scalars in the reals here, I'm doing the reals, and for every pair of vectors, and I'll call them x1 and x2 here, and I'll put subscripts so you don't think I'm squaring anything because we're going to be doing squares a little bit. Okay, we have the following. I do this sum. Oh, and I need another y in x, sorry. There we go. So I take pairs of scalars, pairs of vectors, and then another vector, so 3 vectors. I do a linear combination on the left. I take its inner product with y. It has to be linear. So it has to be alpha 1 inner product of x1 with y plus alpha 2 inner product x2 with y. Okay, I'm going to do one more thing and then we'll go back and check these two with our little simple definition in Rn. For every vector x and x, the inner product of the vector with respect to itself is non-negative, and the inner product equals 0 if and only if f is the 0 vector. That, let's go back and check that all this makes sense with our dot product thing. Okay, instead of having x, I put a linear combination over here. So I just get the linear combination in the first entry, the linear combination here, the linear combination here, the linear combination here, then I just break it up and I get the sum of the inner product. So sum of two vectors, inner product with y will be the sum of the two inner products. 3 times x, inner product with y, 3 times inner product x with y. If x and y are equal, this is the sum of xi squared, and that's equal to 0 if and only if x equals 0. And it's non-negative no matter what, okay? It can't be negative because it's xi squared. Okay, and then as a remark, A plus B imply that this linearity I have on the left, I also have it on the right. If I do X with beta 1, Y1 plus beta 2, Y2, I get beta 1 inner product X with Y1 plus beta 2 inner product X with Y2. Yeah, so I will do the complex case shortly, and you'll see why I want to do the real case first. No, it's a good question. No, the short answer is when I flip the sides, these complex conjugates show up, and it's a pain, okay? And just as a preview, if I'm going to take the vectors and there's going to be a complex conjugate, so if I want to get the sum of the xi squareds, I need to put a complex conjugate somewhere. And if I can put it on the left or the right, that means half the people put it on the left and half the people put it on the right. Live with it, okay? It's not me. I always put it in the same spot, okay? But when you go to a book, every time you assume you know what the inner is, there's a chance you can go wrong, you have. So we will come back to that, but what I'd prefer to do first is just some other examples, because I want to impress upon you that once we know how to compute the inner product of vectors and set it equal to 0, bingo, orthogonality is now defined. It's just defined. So if I can define this inner product on a whole slew of vector spaces, I've got then a lot of examples that just satisfy this bracket notation. That's how we think. Okay, so examples. A, I think you know the first one. Rn with R, inner product X with Y is just X transpose Y. And it's kind of abusive notation because sometimes the i's are the subscripts of the components, and when we had two x's, yeah, so not nice. Okay. B, let's take a vector space XR where X is equal to R n by m. Remember, that's matrices. Not a G. It's supposed to be an E. It's supposed to be an S. Matrices. N by m. Coefficients in R, right? The inner product of A and B, in this case, is the trace of A transpose times B. Okay, so I now know what it means for two matrices to have a trace that's 0. Hence, I know what orthogonality means for matrices. Let's do another vector space where X is, and I'll take a shortcut here. You guys know what D is. So our continuous functions from some domain, subdomain in the reals to the reals, inner product f and g is by definition equal to integral a to b f of tau, g of tau, d tau. Okay, so now I know what it means for two functions to be continuous. You know, I take this to be minus pi and this to be pi, f to be sine and g to be cosine. They're orthogonal, okay? So I know what it means for two functions to be orthogonal. Yes?
A and B be finite, or do they have to be like infinity?
Yeah, so this, yeah, I've taken a shortcut and I shouldn't have, so D equals A, B. A and B are real numbers, so they're finite, A less than B. Now, you can extend it to minus infinity and then infinity, but then we have to put limits here, and I don't want to do it. You know, they're called improper integrals for a reason, that you have to work really hard to show that they exist. So, and I don't want to do anything that's hard in calculus. I just want to do things that are hard in inner product spaces. And then you guys can go review your calculus and extend it immediately. That's the idea. That way also nobody is freaking out on the exam if they're a little bit rusty on improper integrals, because it's not relevant to Rob 501. Okay? Whatever. Okay. Let's go back to the complex case. So, just make a note. Grizzle pasted it in for us. Let's see, inner product, complex case. Did he do us a favor? Maybe not, but he pasted it in for us. Okay, so we only need this, we will only need this in Rob 501 when we start looking at eigenvectors of matrices, because the eigenvectors can be complex. We're only going to need the complex case when X is Rn, or Cn, excuse me. Okay, that's the only case that we will need the complex case, is when the vector space is Cn. But you may come across an interesting example in a course. So it's nice to know this, but we only need this in one case in this course. That's why I don't want to make a big deal about it. But why it's more complicated is you take pairs of vectors in X, so now the field is the complex numbers. When you flip the order, you have to take the complex conjugate. Now, when you do that, you get linearity on the left, okay? Or you can do the definition and you can put the linearity on the right. The problem is you don't quite get it on both, because if you assume the linearity on the left, you know, when you just flip them, you have to take complex conjugates. So when you work it all out, you have the complex conjugates of your coefficients showing up, okay? So that's just a heads up that it's just a pain. It's not hard, but if you misremember and you forget it, then all your calculations will be messed up in a horrible way. And it won't be true that when you put X and itself, you won't get the, you won't really get a norm, because if you do X times its complex conjugate, everything is nice, etc. So it's just a little bit more complicated. And then once again, in the definition, it's your call whether you make it linear without any complex conjugates on the left, or you can make the definition where this works on the right, and then when you have it on this side is when the complex coefficients show up. It's a choice, and anytime there's a choice, half the crowd goes this way and half the crowd goes this way, and your author paper of your author you're reading is so used to one way that he or she never even makes it clear which one he or she is using. you're so used to another way, you don't even make it clear to you which one he or she is using, and then you guys disagree on some key facts, okay? But that never happens when you're doing the real case. Now, if you'd never asked a question, I wouldn't have put that in, no, so what do you think? I think you would. You see, you know me, you know me. Yeah, so this is just a heads up. We will only need it once, and I will not be trying to dock points off of you on an exam because you get your complex conjugates on the wrong side. That is not my goal in Rob 501, okay? This is just a heads up, and we will use it in one lecture, at least, but not a whole lot. Okay. Questions so far? You got the concept of an inner product down, and these are the key examples. We'll learn more as the course goes on, but these are the most important motivating examples. The standard one you get from Rn. This trace thing, if that's confusing you, if you have n by m matrices, just take the columns and stack them up and turn it into a vector, okay? And then apply this definition, and then compare it to this one. They're the same, okay? But you got to do it yourself. I'm not going to do it for you. It's matrices. You can do it, okay? But this is much easier to do the computations this way than to stacking them all up, but it's the same, okay? In MATLAB, it's fine, okay? So it's conceptually, it's nice to know that's an inner product on matrices, and then this is the same thing on functions. And once you understand that that's really a Riemann sum down here, it's the same thing as this, exactly the same thing. So there's no differences here, there's just different notation. They're all the same thing. Okay, here's the key thing we need. This is called the Cauchy-Schawarz Inequality. Let x r, excuse me, let me add the inner product to it. Bingo, bingo. Be an inner product space. Then for every pairs of vectors in X, if I take their inner product, that is a real number, so I can take its absolute value. And the Cauchy-Schawarz inequality gives you an upper bound on this in terms of numbers you can compute just in terms of X and Y. And it's less than or equal to the square root of the inner product of X with itself and the square root of the inner product of Y with itself. Okay, we'll talk about why that's true in a second, but inner product of any vector with itself is non-negative, so the square root makes sense. Okay, it's not -1 in there. No, 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 no. Even in the complex case, that makes sense. Okay. Oh, I see. I should have put this later. I wonder if I'm capable. No. No. No, don't do it. Please. It's not a whole thing? Oh, anyway. I will fix this after class. That is so embarrassing. Okay, so Cauchy-Schawarz goes here. That is so sad. Oh, and it's all on film. This is what I hate about. The only thing I hate about it, I mean, I love it that you guys can watch this at 2x. You can review for lectures. I love all of that. But I'm too lazy to edit out all the mistakes. Okay? That's what I hate. I'm too lazy. Okay, Cauchy-Schawarz inequality goes here. And I'll fix that. But at magnitude x, y less than or equal to inner product x with itself, y with itself, square roots. Okay, so the cool thing that that's going to allow us to do is that if we define the norm of x to be the inner product of x with itself, this is, in fact, a norm on x r. So the Cauchy-Schawarz inequality is going to allow us to prove the triangle inequality. So here, I'm kind of cheating. As soon as I write down double bar, hey, that's always a norm, so it must be true it's a norm. No, I got to prove it, okay? If I really want this to be a norm, I should show it satisfies the 3 axioms of a norm. So the Cauchy-Schawarz inequality is what allows us to do that. So that's why it's really important. Okay, so let me give you the Cauchy-Schawarz inequality, the proof. It's going to be pasted in correctly. Okay, open. Ta-da! Okay, so this, know it, the Cauchy-Schawarz inequality. Okay, so know the Cauchy-Schawarz inequality, and then the proof, just skip it if you, okay? I'm just putting it there so you don't write down the proof on your cheat sheet for exam 1, okay? There's nothing on exam 1 where knowing this proof will be the key to you passing the exam. I want you to know that, okay? But here's the Cauchy-Schawarz inequality. And so whether it's real or complex, this is just magnitude in the case of the complex. It's not absolute value, because this inner product maps you into the complex numbers. Now, this is a real number because when I flip it, I get its complex conjugate. Okay, the only complex number when I take its complex conjugate, I get the number back, is itself a real number. Okay, so this is real and this is real, so these square roots are fine, but this in general is a complex number, so it's a magnitude. In the case of a f is reals, this can be negative, the inner product, so I'm taking absolute value, but these are non-negative and these are non-negative. Okay, so the proof is just a substitution and a painful calculation, and it shows nothing. You don't learn anything from it. Now, doing the triangle inequality, let's see how the triangle inequality works on the norm. That's more fun. And once again, we'll do f equals r just because when we're learning the concept, keeping track of that complex conjugate part is just, I think it takes away from the main thing we're trying to do. So we would like to show that this thing we put the double bars around is less than or equal to double bar x plus double bar y, okay? Question, yes.
To show that the norm of x in the former page.
Higher?
Yeah.
Mm-hmm.
Yes, to show that the norm of x equals to the inner product of x. Maybe it's the square root of inner product. Yeah.
Thank you. No, it's absolutely true, okay? Yeah, no.
So whenever you write that, you're going to automatically, we're going to automatically assume it's a two-norm, right? Whenever you just write the bars without any subscripts on
But
the...
in this case,
No. Okay, so the question is, should I be putting a 2 here? Because in the 2 norm, when we're on R2 or when we're on functions, it's really this, okay? The thing is, we will do more general inner products yet, and then it will not be the 2 norm, so it's a bad habit to put it there. It would be correct for the early part of the course, though. So I understand the question, and thank you for the square root, because I was going to need that really quickly here. So you saved me. Anything else? Yes, please.
is our proof like general to all inner products?
Yeah.
Saying all inner products are norm.
Our proof is going to show that all inner products induce a norm, yes. And so all of the norms that look like sum of squares come from inner products too. You can prove the other way. It's hard, but if you take a course on functional analysis, there'll be a certain property that when you're in a Hilbert space, and you'll be doing Banach spaces, and you'll say, I've got a Banach space that satisfies this property. Sorry, theorem, you're really working in a Hilbert space, okay? But you just didn't. You just made everything hard for yourself. So we're not going to get into that level of abstraction, but yeah. Okay, so these norms here. And now, because we have corrected the definition of what this norm means, a lot of these calculations are going to be easier. So we noted that if something is less than or equal to something, because the square operation is monotonic, that'll be if and only if this squared is less than or equal to this squared, okay? So this part is true. Okay, so that part is true. Okay. And this is just a real number, and this is just a real number, so everybody knows how to expand that out. So that'll be the norm of x squared plus 2 times the norm of x times the norm of y plus the norm of y squared, because they're just squaring real numbers. Okay. So remember, this right now, this double bar, it's not a norm because we haven't proven it satisfies the triangle inequality. So let's now expand the left-hand side. Okay. Norm x plus y squared is equal to the inner product of x with y and the inner product of x with y. This is why it was super important that when the 2 wasn't here, the half was here, okay? So once again, thank you. So that's the definition of the double bar symbols squared. It's inner product x with y and x with y. Okay, this thing is linear on the left. Let's just use it. So it's the inner product of x with x plus y plus the inner product of y with x plus y. Because we're in the real case and we don't have to worry about any complex conjugates, it's linear on the right. So that's the inner product of x with x plus the inner product of x with y, inner product of y with x plus the inner product of y with y. Okay. Because it's real, when I flip x and y, nothing changes. If it were in a complex case, I'd have a complex conjugate when I flipped it. So that's what makes it more painful. So this is norm x squared. This is 2 times the inner product of x and y. And this is my, I shouldn't say norm, my double bar thing squared. Okay, now, because of Cauchy-Schawarz, two times this inner product is less than or equal to two times norm x, norm y. Okay, missing step. This is not really missing. Two times the inner product of x and y. That's less than 2 times the magnitude. And then that's where the Cauchy-Schawarz is. So I skipped a step. Right, minor plus minus is less than or equal to its absolute value. And then this symbol is inner product x half. This is inner product x half. Okay, so we just x plus y squared, we substitute in Cauchy-Schawarz here, and we have exactly this. Okay, we get less than or equal to this. So, okay, so conclusion, norm x plus y squared less than or equal to norm x squared plus 2 times norm x y. Okay, and then that's if and only if. Which is the triangle inequality. Okay, so that's the hard part of showing that every inner product induces a norm. So this is in fact a norm. The other 2 things to check is easy. Is the norm of x equal to 0 implies x equals 0? Well, the only vector whose inner product with itself is 0 is the 0 vector. So done. And then if I do 3 times x, how does that work? It follows from the definition as well. Life is good? Okay. Am I not in tablet mode? Ah, life is hard. Now I'm in tablet mode. Okay. how does that proof go when you do the complexes? We don't care, but you have it now. Okay, so not responsible for proof when f equals complex numbers. Okay, but this is f equals r or c. Okay, so just make a note that I pasted it in. Now you can see why we didn't want to do the complex case, because you guys would have been, I would have made a mistake, you would have lost it, then we had to keep track of all this, but it all works, okay? So in case you need it, it's there, and then we will need it in one case a little bit farther down the line. Am I playing fair enough with you? What's available and what you really, really, really need to concentrate on? Does that bother you that I say you don't have to know everything I say? I'm not used to being treated with respect, Professor Grizzle. Okay, there's so many things. I want you to just concentrate on the fundamentals. I'm totally convinced, one second, when you get done with this class, you'll be able to summarize it on 3 or 4 sheets of paper if you just think that way. Okay, and that's when you know the stuff. If you have to have all of these notes to know what we did in Rob 501, you missed something. Yeah.
Okay, so on the last group, we started with the triangle inequality, and then we ended with the triangle inequality. So, so we were trying to prove that the inner product induces a norm.
Yes. So, see, we started with a question. Does this hold true?
Okay.
Yeah. No, that's cool. No, if you have that, 4 other people missed it too. We're wondering, does this hold true? Well, we note this will hold true if and only if this is true because of it's monotonic with the square operation. And this is what's magic with these sum of square things. As soon as we square them, this square root thing goes away and life is pretty. And we can do all these calculations, yeah. So that was the question mark, and it'd be even nicer if I did that, okay? Well, it's true if and only if this is true, and then this is the easy thing to analyze. We could have carried through all those square roots, but boy, good luck, have fun, okay? I'm not going to be following you in your madness if we do that. Okay. Other questions? Yeah, okay. I've got some good notes here. Jump to orthogonality. Yeah. Okay, so we've got a lot of power here. We see the inner products give norms. I'll fix this before it goes up on the lecture. And then, once again, we're trying to make sense out of this picture. That if we're trying to solve a minimum distance problem from X to a set where it's a subspace, or find the best approximation in the subspace, you probably build it from things that you measure. This is your unknown state of your robot, and these are the things you have from your sensors telling you where it is in the world. What is my best guess of where the robot is? Minimizing that error. If you formulate that as the distance coming from an inner product, this should be the picture. The error has to be orthogonal, okay? So now I need to tell you what this symbol means. Orthogonal in a general inner product space, and a few little things around that. And then we can start writing down theorems that say, well, if it's a minimum, it's this, 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 and we're going to get these beautiful things called the normal equations And the normal equations will give us, in special cases, A transpose A inverse A transpose Y is our solution. Okay. Some of you are more excited than others. But that's normal, okay? That's normal. We're all human. Okay, definition. It's going to have a couple of parts. Two vectors, x and y, in, and this part I don't really care whether it's real or complex. They are orthogonal. That's the definition. If their inner product is 0. The 0 vector is orthogonal to anything. The question, yeah? Yeah? It's not a very interesting thing to be orthogonal to 0, but the 0 is orthogonal to anything, yeah? Notation. Okay, we write x is orthogonal to y to mean their inner product is 0. That's just notation. It doesn't take really any less things because a bracket, well, I guess there's one less comma to write, okay? Otherwise, it's same number of strokes. B, a set of vectors S is orthogonal if I take pairs of vectors in X that are not the same. That needs to imply X is orthogonal to Y. Okay, so we took the notion of two vectors being like this to a collection. And that collection could have an infinite number of vectors in it. It could have only one vector in it, in which case this condition would be vacuous. Okay? If it has at least two vectors in it, we can check that. Okay? And then C, if in addition, all the vectors in X have norm 1, then S is orthonormal. So, orthogonal, orthonormal. Okay, wish I knew what I was doing to make it do that, but I don't. Okay. Orthogonal or means we take any pair, except of course if the vectors are the same, the only way they could be orthogonal to themselves is if they're 0, so we don't want that. Okay. Then we have orthonormal. So in particular, we could have a set of vectors that are forming a basis, and we could check that they're orthogonal. We could have a set of vectors that's a basis. We could check that they're orthonormal. Question? Let's see. These vectors are orthogonal to one another. And this is, if in addition, means this holds true, and then this. Yep. Maybe I could also have said moreover if. That would be another way to write that. Yeah. So, cool? No? And if you're having trouble with my English, what do you think? We have a broad international community here, okay? So I apologize if it's unclear. So S being orthonormal means orthogonal and this. So let's if and only if orthogonal and norm 1. Okay? Basta. Very clear now, okay? Okay, here's something that no one's going to struggle with, but it's always fun to prove. Pythagorean Theorem. Okay, so you guys are used to the theorem of Pythagoras being I have a triangle of side A, another one of side B, this is a right angle, this is C, and the area on this thing, which is A squared, and the area on this one, which is B squared, is equal to the area on this one, which is C squared, right? Everybody learned that as a, I don't know, 8th grader or something? Okay, if you're from China, 4th grade. We know. We're trying to catch up, okay? We know. I don't know if we're embarrassed or not, but we know, okay? So we'll just leave it at that. Okay, so here's the equivalent in an inner product space. If X is orthogonal to Y, then the norm of X plus Y squared equals norm of X squared plus the norm of Y squared. Okay, and you know, I'm not trying to do a con job. I'm just trying to avoid a whole bunch of unnecessary concentration on complex numbers. So, norm of X plus Y squared is by definition the inner product of X plus Y and X plus Y. Okay, so these types of expansions, we want to start doing them quickly. So what we see, we have X inner product with X. We have Y inner product with Y. But then we get X with Y and Y with X. But both of those are 0. Okay? Equals inner product X with X, inner product Y with Y, plus 2 times inner product X with Y, but that's 0 because X is orthogonal to Y. A lot less work than Pythagoras had to go through, okay? He didn't have this notion of orthogonality hanging around for him, okay? So how are we doing? Inner products, you're kind of surfing them? Question, please.
So in this proof, we sort of assume that, or we only show that true for all norms that come from inner products. Like you mentioned previously that all norms can be expressed as inner products.
No.
No, that's not true?
That's not true.
Okay.
Yeah.
So then, only true for inner product norms.
Yeah, okay, so let me rephrase the question. When we're working in an inner product space and we write down this symbol, it always means the square of it is inner product, inner product. That's the definition. So as soon as we write down we're in an inner product space, that's the norm. It's no other norm. Now, if I'm on R7, I could write down 256 different norms. But the one I'm using is I need to tell you what the inner product is. Now, there's 257 different inner products on Rn, but each one of them will always satisfy this. But there's a ton of norms for which this is not true because I have no notion of what orthogonal is. So only norms coming from inner products are associated with a vector space that has a structure where this makes sense. Now, you could say, well, I will say two vectors are orthogonal if this inequality holds, because I need this to be 0 for that to hold, right? So that's the thing you could do in an abstract norm space and play games, but then you could go back and prove that this norm comes from something like this. So almost no norms satisfy that, okay? So don't let that will not be a question on an exam, but so inner products are special. Okay. There's lots of norms. Most of them do not come from inner products. Minimum distance problems that come from inner products give you least squares things, and the answers are easy. They're essentially linear problems, as we will see. You don't know what the word convex means, but you will before we're done with this course. They're the simplest possible convex problems. Life is good as soon as you have an inner product. Okay. Oh, that was not a double question. That was stretching. Okay, no. It's like, wow, I'm really in trouble now. I've got a double question coming. Okay. Projection theorem. So this is not quite the projection theorem. So this is a huge, huge thing. Let X, R be an inner product space. Let M contained in X be a subspace and X just some point in X. Okay. So pre-projection, we're going to have to do a couple more things to get to the real projection theorem, the one we want. But this is pretty exciting. It ties our tools together. If there exists a point in M, so I'm going to call it M0 to make clear it's in M, such that the norm of X minus M0 is less than or equal to the norm of X minus M for every point in M, then M0 is unique. Oh. Okay. So, if this holds true for every point in M, then this is a minimizer, right? Okay. So what this says, there's either one or maybe there's none, but there's not two, okay? It doesn't say there is one. It's either one or none after this. There's not 17, there's not 14, there's not 2, 1 or none. Okay. Okay, I don't have the power yet today to prove that such a thing exists, but I can show you that if there is one, there's not a second one. B, a necessary and sufficient condition that some point in M be a minimizing solution. And I'll call it a vector just to be clear that it's a vector. In M is that the error vector is orthogonal to M. Okay, I'll write down the formula, but that is x minus M0 orthogonal to M. Yes. Okay, so this is giving us a ton of information. It doesn't say that we can always successfully find one. Okay, but the property we want to look for is this picture that I showed you in R2. The error vector is orthogonal to the approximating subspace, okay? This pre-projection theorem is the mathematics that says that picture holds in general inner product spaces. So that's huge. That's huge. We will be able to show in all finite dimensional vector spaces that that M0 exists. So that's the other thing we'll do. All of this stuff here is true. It doesn't matter whether the vector space is finite dimensional or infinite dimensional. We just don't care. We never say. And what we will say on the projection theorem, assume X is finite dimensional, then we get the rest of it. So that's our way of doing it. Quick picture on the importance of the 2 norm here. Okay, so here's some axes. Here's a point. That's a subspace, man, okay? It's not a manifold, it's not wiggling, that's a subspace, okay? Now, hopefully it's at a 45-degree angle too, it's pretty close. Take the norm of X as the 1 norm. Okay, this is X. Okay. Oh, I don't like my angle here. There we go. I think that works for me. Okay. So this line and this line, that's shorter than this line. Okay? This is the 2 norm solution, right? Orthogonal. But what is the 1 norm of this error vector? It's 1 plus 1, 2. Oh, what is this? This is 1, And then this is 1 over square root of 2. And also, there's 2 of them. Okay? So, you change the norm. This is not the minimizer. This is the minimizer, and it's not unique, okay? So it's magic in the 2 norm. Okay? 2 norm is important, okay? So, non-unique minimizer. Okay, it turns out the 1 norm and the infinity norm are bad. If you use the 1.001 norm, it's also unique again, and everything in between. Okay? You'll prove some of that in homework. I don't want to get in the middle of the proof, so I think what I'd like to do is just see if you have questions. And then since I skipped office hours on Wednesday, I felt badly about that. Then I'll invite people up to ask questions on homework too after class here, okay? So instead of getting into the middle of the proof, the importance is these 2 are minimizing solutions. So you might write X stars next to here. The norm of the error is 1 plus 1 over square root of 2, whereas this one, the norm of the error is 1, 2. And 2 is bigger than 1 plus 1 over square root of 2. Sorry, okay? Yeah. So X star, that's also X star, and 1 norm of X minus X star in each case is 1 plus square root of 2 over 2, which is strictly less than 1 plus 2. And the norm of X, which is the norm of X minus 0 in the 1 norm, is 1 plus 1. So, okay, I'll just take the time to update that. So it doesn't matter which of these X stars you take, this is the answer. And 0 is not a minimizer, it's 2. Okay? So this pre-projection theorem, which we'll jump right into that on Tuesday, that is super cool. There's either one solution or none, and you characterize it by this. And this yields simultaneous linear equations. It's crazy, okay? Absolutely crazy. Okay, we're done. Thank you.